Hello, everybody. How's everybody doing? I'm just gonna leave the headset like this because my hair's wet. So, but can you all hear me clearly? Yellow. All right. Good. It's a bit quiet. Okay. I don't know. This is a microphone that's been here for 2 years and I haven't used it. It's like a gaming headset. Some HyperX something, whatever that might be. Okay. I'll keep it like that so it's close to my mouth. I'll maybe like 10 minutes or something when my hair's dry because I just showered. Uh, I'll put it on. Okay. So yeah, I mean this is very Dune-like, anyways, having this like this. So welcome to the Mexican edition of CS302, I guess. Uh, as you can see, I've set up everything to be the same. So other than the background being different, and the audio being probably better that it's like this because it's less echoey. It's probably better for you, anyways. So, but yeah, I still have everything set up the same. So, yep, we can get started. I have a tablet here. So the only difference, the camera is a little bit not at the height, so it actually will work out because when I lean down, you'll see better. So I'm just gonna move my keyboard out of the way so that I can manipulate this because we don't really code in this. That's what I need more for the 202 where I'll need the keyboard. So hope you all had a good weekend. I can see that we have a question on assignment 6. For the write-up in assignment 6, it asks us to type out the 4 messages. I thought there were 5 to print out. I think maybe what I meant was maybe write all of them, even the ones that like all 4 traversals per message. Maybe that's what I meant. Let me take a look and see what it says. By the way, I hope the internet connection's okay. I mean, I have fiber here, something I don't have back home in Vegas, sadly. So this should be actually better, but we'll see whether it's truly stable. Assignment 6. Okay, that's good. We'll see if there's a delay as well. All right, so looking at assignment 6. I'm looking at the write-up to see which question you are talking about. There are 4 messages you see when you run the program, meaning the traversals in one specific form will create a message in English. Why didn't you report what these 4 messages are? Oh, I know why it is. I think it's because I give away one of them, if I recall. So even though I put 5, I think I give you away what the first one says somewhere. I think. And so that's why I'm like asking you to put the other ones. But if you want, just put all 5 to be safe. But I'm pretty sure that somewhere in the sample code, I give away one of the answers. Because, so you can understand like what it means. So that's probably why I'm asking for the other 4. But yeah, you can go ahead and put all 5. Actually, or you know what? No. Actually, I think what I did was one of the traversals is random and doesn't build a message maybe, and then the other 4 do. I think so. I don't remember, but just if you find 5 real messages, you can put them all 5 and it's fine. You're not gonna get deducted. So yeah, okay. So maybe that's it. Maybe one of them doesn't have a message. Okay, that's what I thought. So yeah, I have fiber from CenturyLink in Vegas. Yeah, I know. Where I live, literally like across the road from me, like maybe 200 feet away, they have fiber. So it's just my community group doesn't. I guess it's very sad. It's probably because of the build date. As for the extra credit, I think I said I would do that at some point. That I would discount it, and I think I might have already done that. I said I would discount it the equivalent points that for the 2 days that I wasn't there. I'll look back at check the campus announcements on that for the 2 days I didn't stream. When I announced that, I said I would lower the extra credit for those 2 days. I don't remember the exact number. I did the math. I think it was like 500 points cheaper. But well, yeah, it's still like it's still 10.3. But well, actually, I'll check that. I'll check that. But I'm pretty sure I said I would lower it. So if I haven't lowered it yet, I'll lower it. But yeah, don't worry. Just don't redeem yet, I guess. 500 points in the announcement. Yeah, so I'll lower it. I guess it'll go to 9.8 then. I don't I have that easily accessible in Vegas. Here I have to find the link to that. Viewer rewards, channel points. Either way, I'd want you to wait till the end of the semester to redeem it. So here. So that would be 9.8. Okay, so I think it's updated now. But I don't know. You tell me. So okay, the write-up has a maximum page count. I think there is a maximum page count. Check the canvas, cause and that's not because we're trying to be like evil. That's just because the TA has to grade a bunch of them. So definitely don't write more than you have to. But I mean, pictures, it's okay if it's pictures. I think the TA is just mad if like it's a bunch of text. Pictures, if you go over because of pictures, it's okay. Because pictures, like he just looks at them, it's like okay. But if he's got to read like a book, he's not gonna be happy. Okay. Anything else on the assignments? Are we doing okay? When are they due? So they're due. Oh, is it tonight? So are we good with that? Are we all gonna be able to make it, or do we need more time? I want to make sure that you're all gonna bomb it, especially with the AVL tree. More time? How long though? When is the AVL tree assignment due though? That's the one I want to make sure that they don't overlap too much. Because I mean, I can give you more time, but I wanna check when that one is due. This is weird. I don't know if it's the stream, but like Canvas is really slow. Like other websites are fine, but Canvas takes a while to like open anything. It's kind of annoying. 48 extra hours. Okay. So I'll shift them both by 48 hours then. The ABL one, that's the one I'm kind of worried about. Uh, November 3rd. When is November 3rd? Okay, so maybe the ABL one will be moved to the weekend of like November 6th. Beware though, November 6th I will be busy because I'll be flying back. But okay, okay. So then I'll move it to. Oh, that one has like a rubric. That's kind of cool. Today, okay. So I'll move it to Thursday then. So it'll be Thursday and Friday then, since they're both due at the same time. But like one's due 24 hours later. Uh, because I assume by now you've noticed that they're basically the same assignment. It's just that extra function that you have to do. Well, it's two of them, but like once you build one, the other one is pretty simple to do. You just copy paste it and then like swap the pointer instead of going from one side to the other, going this way. Okay. Uh, I will try to do that right now, but no guarantees that Canvas will cooperate with me. And then the AVL one will probably push back into the weekend, like I said, November 6th, but I won't do that right now because it will take forever. Like literally, I'm just waiting for this to load right now. The ABL one will be one of the hardest that you do because not actually, it's not hard to code it. It's hard to debug it. So it becomes a long process that you have to do because the rotations, like it's a lot of pointers you gotta move around. Like when you transfer the childs, you'll see today. But that can get pretty nasty. Okay, so all right. I don't want to talk while I do this, so I don't mess it up. Okay, hopefully I did not screw up the times there. So there's one of them, and then the other one. Okay, and then you guys can open up Canvas if you want to. to verify that I got switched. I don't know why Canvas is so slow today. I know it's not my internet because everything else is fine. That's why it took me so long to open up the assignment to answer the question. Okay, so I think the deadline has been. There's 6 submissions, by the way, in case anyone's curious. But then again, most people submit last minute, so I'm not surprised. Okay, so now it says it's due Thursday, 11:55. Notice it's 11:55 and not 11:59. I don't want to switch out to 11:59, so I don't want to go back and edit it. So just be aware of that. And then the other one is the 29th. Okay. Yeah, so something's up with Canvas. Okay, so the AVL one, you guys can remind me next class, and I'll update the deadline on that one. But actually, you know what? For the people that are not here, maybe not updating it is a good thing because that motivates them to actually like start it if they haven't. So, okay. Um, yeah. Okay. So it's probably well, you know, yes, there's probably a bigger ping now because I am literally far away, so there could be that too. But okay, I'm not gonna touch Canvas anymore because I don't want Canvas to screw up the stream. But like I said, remind me on Wednesday, and we'll talk about the AVL one. Okay? So yeah. All right. Let's start then. This is hot. Okay. All right. So let's kind of review what we did last time. You know, I mean, hopefully some of you tried to do this rotation on this example, but let's go back further. So we said that, you know, the idea behind AVL trees is that we want to have a tree that we can actually access. Any node in the tree we can access in log n time, right? Because it's a log n height. Uh, oh, very fun. Well, yeah, but that's the extra credit, so big deal. I can't extend the extra credit though because we have the deadline of the paper, so like we have no choice on that. Uh, you know, that one's like we're stuck. Like I wish I could extend it, but we have the paper's due on the 5th, but we have to submit it to the proofreader on the Monday. So we're gonna take all your surveys and then work through the weekend on doing it. So yeah. By the way, very quickly on that, if you haven't done that yet, when you're doing it, if you see that the arrows are really off, it's possible that the OCR scanned the wrong room number, like it misread it. I've noticed that it's reading 361 as 316, and so it's getting confused. If you see that, you can try rerunning the OCR uh, by like closing the app and reopening it, and then see if it works. And if it does, just include the count into your how many times did it fail scanning. I should have in practice, like you know, it's always nice to see things in retrospect. I should have included a button that says this is what the OCR read, so you could confirm that that's actually where you're at. We will do that in the next version. But yeah. Anyways, yes, try refreshing everything. If you have issues with Twitch, I have everything closed. So, and I've explicitly told people here not to use the internet at all. But like I said, I have fiber here, so it's not particularly that. Probably the distance. Anyways, going back to this, like I said, we have AVL trees that we're using because we can access every single item in the tree in log n time, and that's insertion, extraction, so retrieval, and then also modifying it, right? And there's more than just like searching for something, because like to confirm something is not there, you have to hit the leaf node of where it would be. And so that's what we're really trying to do. Okay? We are trying to make this tree log and height. And the way we can do that in a tree based on the properties of the trees is by keeping the tree as full as possible to have basically everybody have 2 children, you know. And so that's where this balance thing comes in. And so we said, okay, we're going to think of height as a left and right height for a node. So when we have a node like this, we want to compute the height. We're going to define height of 0 to be a node that has no children, and then height of 1 to be a node that has 1 children, height of 2 to be a node that has 2 generations, like a grandchild. Okay, but of course, this node on this side has 2, but on this side has 1, right? So ultimately, this is a height of 2, and this is a height of 1. Okay, and so that's what we did last time. And then, you know, we said the rule is that if the difference between the left and the right, the difference between the left and the right is greater than 1, so it's like 2 or more, then that's considered unbalanced, and we have to balance it. And how to balance it is performing the AVL algorithm. AVL being by the two Soviet, well, I don't know if both are Soviets, but one of them was Soviet mathematicians, and it's to perform a couple of rotations, and those rotations are done so that the tree is balanced. And you will see, an unbalanced tree will kind of, when they even out, it becomes a little shorter, and that's the whole point. So those rotations are done as you insert information. So you don't. It's not like a sorting algorithm where you just throw all the numbers in and then you run quick sort. No, here it's more like you're organizing things as you put the numbers in. And the reason you do that is because if you don't, trying to actually organize the tree when it's finished will take a long time, and you lose that log of n property. Okay, so we showed you last time, or I showed you last time, two kinds of rotations, and those were two out of the four that we really have. Although I also said that the rotations are all the same. Like in reality, even though it's four rotations, it's just one rotation done in different ways. And the obvious example is the first one. So that I showed you. So I said this is a left rotation where we're taking. You notice it's cutting off. Uh, it's cutting off the right side of that. Let me see what's up with that. Maybe I need to move that. I don't know why it's cutting off that piece. Hold on. I see this. Okay, that's fine. So let's just shrink this a little bit. There we go. Okay. That way I don't like start drawing something and you don't see it. Okay. Let me just switch between them really fast. And then I think I just have to bring this up. And now we're good. Okay. So going back, like I said, we have just one rotation that you do different ways. And so, for example, here, what we're doing is we have a tree on the left here that is heavy. And if you, and always think of holding it by the root with a string, and if it kind of goes towards one way, probably it's unbalanced. And so here we have X, Y, and Z, and as you can see, this tree is very, very, very like right heavy, right? We have all of these things on the right, and we only have one node on the left. Or we could have nothing here, because remember, these are like optional children. So if we just have the three nodes here, we have all these here and nothing here. So when a tree is right heavy, you want to take things from the right side, which is the heavy side, and put it on the light side, which in this case is the left side. So you want to bring things this way, and that's basically what's happening here. The mirror of that is also true. When you have a tree that is left heavy, then you move things to the right, and you do that right rotation. So as you can see, these are both the same thing, and that's pretty much what we did. And so before I show you the next two today, I want to bring you up to an example that we had, which was where we were inserting and balancing things here. And so far, when we had something unbalanced, we performed one of these two simple rotations, and the problem was solved. Like solution solved, and everything was great. But here's the issue. Suppose that you have something like these three numbers that you want to insert. Okay, you want to insert 1, 3, and 2. When you do that, if you try to do a single rotation, let's see what happens. So when we insert 1, there's nothing else in the tree, so basically we consider this to be height of zeros. It's balanced. When we put in the 3 has to go to the right side because it's bigger than the 1. And so now we have 0 here and 1 here. That's a difference of 1. We said, absolute value or whatever. Still a difference of 1, which is not unbalanced. 1 is good, 2 is bad. When we put in the 2, though, it's bigger than the 1, so it has to go to the right side. But we already have a 3 there, so now we have to put it on the left side of the 3. And so you end up with this 3. After you finish inserting something, you're going to check the height. And so here you're going to see that this is height of 0, 0. Here it's a height of 1 and 0. And then to compute the height here, on the left side it's 0. And on this side, you take the biggest of the two numbers here. So you take between 1 and 2, you take the 1 because it's bigger. You add 1 to that, and you end up with a 2 here. And now we can see that this is a difference of 2, which is a bad thing. It means, well, it's not bad, like, ooh, we screwed up. It's more like, well, it just means we have to rotate. We have to balance it. So you're like, okay, you've learned these two rotations, so you should intuitively try to use the rotation to see if it would fix it. So is this a left heavy tree or a right heavy tree? Well, if you're holding it from a string here, on this side, we have nothing, right? So there's no weight there. But on this side, we got everything, right? I mean, it's kind of twisted like this, but it's still technically all on this side. So that means that the tree is very heavy on this side. So we got like some vectors. That's, kind of what it would look like per se. And so this is going to be considered like a right heavy tree. So if it's right heavy, we should fix it, with a left rotation, right? So let's try and do a left rotation and see if that works, which of course the reason I'm telling you is because it's not going to work, but let's actually screw up so that we can see when the single rotations will not work. So, all right, let's take our algorithm per se and try to apply it. So I'm just going to copy it. I have it over here on the right side, but I'm going to copy and paste it here so you can see it. I'll just make it a little bit small. But okay, so this is what we're trying to do. And so you kind of have to, put these numbers where they would fit. So actually, you know what? Let me bring this higher. Let's try and kind of plug in the numbers where we think they would go. So for example, the 1, is kind of where the X is. I'm going to throw in a 1 there. Use a different color. So the 1's kind of there. Then the 3 is where the Y is. And then the 2 is kind of where the 2 is. Oh, that's kind of coincidental. And then we don't really have a Z, right? So you can just kind of erase that from here. So, and we also don't have a 1 here. So that's kind of where it is. So that means that we have to take our, our X and our Y and put it so that it matches that, right? So that means that based on our algorithm, this was the X, this was the Y, and this was child 2, right? So that means that the 1 should go here then. And then the 3 should go where the Y is. And then the 2 should go where the 2 child is, right? So here. And then nothing else is actually exists in this tree, so we can get rid of it. And so look at that. Using that algorithm, obviously you don't have to do as much detail as I did, but I wanted to do that because it's the first example. But you can see how we started out with this on the left, and after doing the rotation that should fix it, it kind of just made a mirror image of it. I mean, the numbers did swap. Like the numbers, all the numbers basically swap. It's still binary search because as you can see, the 3's to the right of, well, in the beginning, the 3's bigger than the 1, so it's to the right. In the end here, the new root is the 3, so to the left of that is the 1 and the 2, 1 and then 2. So it's still like actually legit. Like it's still a binary search tree. It's not violated that property, and that's one thing that's important to know. When you're doing your rotations, never ever should, after you do a rotation, screw up the ordering of the numbers that is no longer in binary search form. What I'm saying is, if you got a 3 of this format, never ever will you see something like this or something like this, because these violate. Actually, well, I stand correct. I stand correct. This one's actually okay, but that one's not okay. Okay, that one's not okay, and then this one's not okay. So these are bad, right? You can see how these are bad because they violate the binary search property, whereas these are okay, right? So if you start with any of the 2 okays, you should never end up with the bad ones. That's kind of what makes the algorithm robust, that you don't need to worry about that. But anyways, so even though we did not end with like a bad rotation where things are out of order, we didn't fix the original problem. Hopefully you don't hear me like drinking there. Get the microphone close. But yeah, we didn't fix the original problem. Like if you go ahead and measure the height of this, we have 0, 0, We have 0, 1, and then 2, 0. So we took a right heavy tree and made it into a left heavy tree, but didn't fix anything. And if you try to like rotate again, uh, sorry, I was looking at like some. It's kind of blinking, connecting to chat, so hopefully everything is okay. But yeah, let me know if the chat dies or something. But yeah, so we took what is essentially a tree that was like heavy on one side and now it's heavy on the other side, and we're still kind of stuck in the same situation. Not quite ideal again. So we can try another rotation. In fact, now that we have a left heavy tree, let's try a right rotation to see if it fixes it. You know, just like when something doesn't work, the best thing to do is just try it again and see if maybe the second time it works. So this time, we have this and we are going to rotate it again. So basically what's going to happen is this is going to end up like this. Obviously the numbers will have to be rotated. And then the child has to be transplanted from here to here. Whoa. Child's like, I am going on my own. And as you can see, when you do another rotation, which in this case is a right rotation, it's always good in the arrow to put the rotation you're doing so you're explicit. As you can see, we actually ended up with what we started with. So usually this is actually not a coincidence. This is pretty good property. Yeah, I can put the headset on now, I think. No, no. So what? This is a pretty good property. When you do your rotations, if you do the same, if you do like a left rotation and then you do a right rotation on the result, you will end up with what you started originally. And this can be a good thing because if you perform a bad rotation per se, you can undo it by just calling the opposite rotation, the mirror one of that. So, okay, we've got it back to where we started, but we still have not solved the problem. We still have a tree that's unbalanced. And so, as you can see, there are going to be some scenarios where the single rotations are not going to help us much. So, what do we do in those cases? Well, we need to perform what's known as a double rotation. The double rotation, as the name implies, is basically doing two rotations on the problem that we have. Now, we did two rotations and we ended up what we started with. So it's not just like you just do two rotations and call it a day. What you do is you do a rotation first on the grandchild and the parent, and then you go back and do a rotation of the simple ones on the actual original root. Okay? So to kind of write that down and then I'll show you examples. A double rotation is going to be a rotation that you can do when the single rotations fail. How you do it is rotate, do a single rotation on the child and grandchild. It's still just a single rotation between them. Or maybe I should rewrite this, say, do a single rotation between. Yeah, I'll say between instead of on. So do a single rotation between the child and grandchild. Okay? Ah, dang it. Let's bring that down here. Okay? So do a single rotation between the child and the grandchild. Then do another single rotation on the root node that was originally unbalanced. And I would appreciate if you guys like give me an occasional heads up that you're all still alive, because again, I'm kind of worried that the connection might have died. But it says live. Ooh, wow. Ooh, there's a massive delay on my end. I'm still writing on the screen there. Okay. But all right. So if this makes no sense to you, don't worry. Once we do the examples, it'll make more sense. Okay. So before I show you the property, I guess like that, let's just fix this problem one first. Okay. So we got the 132. So intuitively, you should be able to see what the solution to this should be, right? We got to make the 2 be the root. That's the one that we really have to do, because then we can put the 1 on the left and the 3 on the right. It's a bit quiet. Let me put a headset on. I think now I'll be okay, because then I can bring it up. And then let me try to boost the audio here. Ooh, it's already boosted all the way. All right. Hopefully it's a little better now that it's closer to my mouth. Okay. But or even like this is better. Okay. So ultimately, you know what the answer should be here, and you kind of just have to understand how you get to the answer. And so, as you can see, doing a rotation on what I would consider to be the root problem, which is this one, because this is the actual imbalance. This might not be okay. Great. This might not be like the real root of the tree, so there could be a bunch of stuff up here, but that's okay. The only issue here is in the one, and so we don't care what's above it. What's above it's not going to change with our rotation. It's not important also to know. So you're like, okay, you know, we know that we have to fix from the one down. But instead of trying to do rotations with the one involved, let's kind of let that chill for a little bit and then just worry about the child of the problem and the grandchild. And let's rotate that. So basically, let's rotate that with a single rotation like that. And then after we do that, we can actually perform this rotation and bring the one down like that. Okay, now I know the numbers are all upside down, but you get the idea. All right, so just as long as you rotate them back. I'm just gonna erase them and rewrite them because it's too much effort. Okay, so again, let's do the replay of that action move there. What was numbers 132? We're gonna perform a rotation on these guys, which by the way, when you do that rotation, it might make the tree temporarily more imbalanced. But the one exception where you're just like you just don't even count. You don't look at the heights. You like blind for your eyes if you're doing a rotation. Do the second rotation and then go ahead and check. Okay? So the idea is that we don't like this like Pac-Man looking shape. That Pac-Man shape means double rotation. When it's a straight line like this, that's a clean, simple rotation. However, these are examples that have no children involved. When you get children involved, the shape might not be so obvious. That's why we have the algorithm to just try things out and do it themselves. Okay? Sorry, there's a little delay there. Okay, so let's go ahead and look at the general case of the double rotation. So we have what's known as a left-right rotation. The reason it's called that is because first we're going to do a left rotation on the two nodes here, so the child and grandchild. So we're going to do left rotation, meaning we're going to go this way. So this way. So we're going to take the Y and we're going to bring it down like that. That's going to be one rotation. And then the other rotation, once we do that, we're going to end up with this. As you can see, it's just a single rotation. We're just not touching the Z. We're doing it on the ones beneath it. That's the first single rotation. And then we're going to do another rotation, which is just going to be your standard right rotation. Okay, so basically, the first rotation is to fix our problem, And then the second one is just to do the normal rotation that we're used to that will balance the tree. How do you know this works? After you do them both, you check the tree and it's balanced, you're good to go. Never, ever, ever should you have to do more than this. So you either just do a single rotation and fix your problem, or if you have to do this double rotation, then you do the double rotation and it should also fix your problem. You never should run into a situation where like you do a double rotation and like you kind of fix it, but it's not fixed yet and you got to do more rotations. No, it should always just be one. And that's why you always do these rotations, like, or at least you check for the height being balanced after each individual insert. That's what guarantees that you only have to do one of these rotation sets per node that you insert if it becomes unbalanced. Okay, that's the left right. The right left is just again the mirror version of that. So if we have something in this shape, which you could see when we try to rotate it, we actually ended up with that. So that was a 3-1-2. Here's what you would. Here's the visual way of doing that. So 3-1-2. What we're going to fix first is going to be these. So we're going to just take this and do the single rotation like that. And then after that, that's obvious. That's a simple example. We know that all we got to do is just rotate that and we're good to go. Okay? If this was in person, I would love to bring some strings with numbers on them. Then I think it would be pretty cool. But yeah, I guess I could make them here, but little crafting involved. But yeah, so those are the double rotations essentially. There's no rocket science to them. And like I said, these are all basically just that single rotation of having something in the shape of this and putting it in that shape, like going from that diagonal to this. And all the rotations are the same thing, just either the mirror version or doing more than one rotation in the same node, but it's still the same one. That's why like when I started talking about AVL trees, I told you like you don't have to heart rote memorize these things. You just have to understand them and see how they're all the same thing, and you just know which one to apply. But when you're coding it, it is nice to actually code all four cases so that you can just do a function call for each one. And then of course you can debug all four separately, which is how you should do it. Don't try to debug them all at once. That will not be fun. And then and then you can make sure that all rotations work, and then you can actually run your algorithm. So if I were you, step one, which I believe you have done in the previous assignment, is be able, or have you? Not really, but step one would be to be able to just build a binary search tree, which is just a standard one, without AVL involved. Once you have that working, then start each of these rotation functions. Start with the most basic one, the single rotation, and get that working. Then do the mirror version of that, which should be very similar in code. Then do the double rotations. The double rotation function should be its own function, but you should be calling your individual functions on the right nodes. You don't have to recode them. You can if you want, but I would just call the other ones because you know the other ones work because you already tested them at that point. And that's how you build the double rotations. As long as those double rotations are robust, doing the rest of the code should be practically a piece of cake. Where it becomes hard is if you try to do everything at once and then test everything at once, because then it just becomes basically a what you call it a hunt for the bug. You're trying to find a needle in a haystack kind of thing. You got so much code that the issue could be anywhere. So break the problem down and do the pieces separately first, then put them together. That will be your best approach to programming. Not just this, but like life in general. Don't try to code like a million lines at once and then try to run them and see a million errors and then just weep in silence. But yeah. Okay. So now that you know all four rotations, let's just go ahead and do some examples so that we can basically make sure that we understand them. Okay. So for the rest of the class, I am literally just going to go through a bunch of examples. And again, this is on video. What video is this? 15 and probably 16 if I was to guess. Yeah, video 15 and 16 of last what is this fall, probably fall 2020. I do more examples. So I'll remember to leave on the description below a link to those if you want to see more examples. I guess they were Star Wars themed because I did Obi-Wan and Anakin inserting into a tree. So I don't want to do the same ones. I'll do different ones. That way, like by like 2 years from now, we have a ton of examples. But yes, if after today you still want to see more examples of rotations, or maybe before the test, I welcome you to watch those videos to uh, to see that. Well, no, for the AVLs, I believe it's 15 and 16. So 15 appears to be one based on Anakin, and then 16 the Obi-Wan. Okay, so check those out. And then, like I said, I encourage you on the test to have this right here as a cheat sheet. Okay, of course, you gotta practice before you do the test. You gotta practice. On the test, you're not coding it; you're doing it by hand like I am. But if you don't practice it, it's gonna take you a lot of time to do the rotations and very prone to mistakes. And then you're gonna you're gonna run out of time on the test. So you gotta not just understand it, but do get a little practice in. It's like workout. Do your AVL exercise. Okay. So let us go ahead. You know what? Let's continue with the Star Wars theme from last semester. Except let's do different ones. So go ahead and give me like a character name, and do be aware that if you give me a really long name, we're gonna be here all day. Maybe we'll just do part of it of an AVL tree that we're gonna build. Okay? So give me a character name that's not Anakin or Obi-Wan that you would like me to insert into this AVL tree. This probably the stream delay doesn't help. Sad. I'll wait a little bit. I'm gonna turn off the my own view of the stream so that I don't use that bandwidth. Oh wait, no, but if I close that, it might. Yeah, I'll just hide the preview. Hide player. There we go. Yoda and Vader. Okay, I like those. We'll start with those. Cool. All right. So we're gonna actually put them both in the same tree. Or actually, yeah, let's just do it like that. And then Chewbacca. We'll do Chewbacca afterwards. Because four letters is very little for rotations. If anything, we have like one rotation if we're lucky. But we'll do it like that. So we'll do Yoda, Vader, and Chewbacca. Awesome. All right. So yeah, I mean you can always combine them. Let's uh let's start out with the Yoda Vader one as well. So we're doing AVL, so we're inserting, we're using this alphabetical binary search tree style. So when you first insert something, the first time you're never going to do a rotation, you know. And so ultimately, you can check that because it's part of your code, but nothing's going to get very exciting until you insert like the third item maybe. So when you see the O, and you all probably should correct me because I might screw up the alphabet, but I'll try not to. Not really that it matters much if we put something in the wrong spot. I'm not taking the test, but still you want to triple check your alphabet when you're taking the test. Okay, so you put the O's before the Y, so it's going to go there. So now we have a height of 1. It's still balanced. Uh, we're going to put in the D, which is going to go first. So now you can already see it that it's going to be unbalanced, but I want to kind of show you because it's the first example. You can see there the 2, 0, it's unbalanced, so it's left heavy. So we're going to do a right rotation. So as you're writing this, if it was a test, then make sure that you actually write something like this. So you do that, you put an arrow, and then you put the rotation you're trying to do. This is the right rotation. And then you put the result of the rotation, which in this case is going to be that. When we do a double rotation, I'll do slow. But this one, we already did single rotations last time. So plus those are pretty, I mean, it's kind of, it starts to become intuitive after you do it a couple of times, right? You basically just take this middle node and that becomes the root, and then stuff to the left, this to the right. And again, one very good way that you can double check when you're doing this by hand is that you can actually see if the tree properties still remain. So like, if O's the root, then the left stuff has to be smaller and the right stuff has to be bigger, right? So, and also, by the way, this is something that I want to emphasize just because it might be obvious to me, but not to you. When you're coding your assignment, write a very simple example like the one we're doing in class, because you know exactly what rotations are supposed to happen and when they're supposed to happen, and then do it. And then print the tree after every rotation so you can see if the tree looks right. You have a function to print the tree from the previous assignment, I think. So, or at least a traversal of the tree, which you can do by hand to double check, right? Like I could do a traversal on this tree right now and compare them. And that way you know if it ever the traversal is not what you expected and you know that the traversal code is correct, which it should be because that's not that hard and you've done it, then you know something's wrong, right? So it's that concept of doing things by hand that'll be good for you. Anyway, all right. So let's insert the A now because we, after the rotation, we check, we see that it's balanced. We're in business. We can keep going. So let's just keep inserting until we gotta rotate again. So in this case, the A is gonna go here. We're fine. We don't have to rotate. There's a difference of 1, which is still okay. It's only when it's 2 that it's not good. So we can keep inserting. So now we got the Vader part to insert. So I'm just gonna bring the word Vader down here. Okay. The V, where does the V go? Okay, the V is gonna go here, right? So greater than L but less than Y. So now we got 1, 2, 1, 0, I mean, and then 2 here. Cool. Even more balance. And I said this before, but I'll say it again. The trees, whether they visually look balancing and they're balanced, is a good rule of thumb. But there are some cases where like things may not look so balanced, but they are. Case in point, this looks kind of weird. Doesn't look really balanced, but it technically is actually perfectly balanced. So yeah. Okay. We got another A to insert. We gotta make sure, when you're dealing with duplicates, you gotta be careful with these algorithms. Bad things happen. So again, commit to the same rule that you're doing before, which is if you have a duplicate, put it as if it was a smaller number or letter. So in this case, it would have to go to the left of the A. Doing that and sticking to that rule will avoid bad things from happening. But, you know, yeah, that's all I'll say. AVL and duplicates can get buggy, so I will warn you. Uh, I probably won't put on the test a duplicate, but when you are testing in your code, you know, be careful of duplicates. I think when you do rotations, things may get screwy. When we're doing them here, we'll notice that, but when you're doing it in code, just be aware of that, okay? It's not very nice and safe with duplicates. So, I mean, I kind of hope we screw up right now because we would see that, but we might not end up seeing that. Okay, so we got the V and the A, so let's keep going. Oh, wait, no, we gotta check the height. Aha, yeah, we're on balance, right? So we're on balance on these three. So again, those are the ones we gotta touch. Don't touch anything here, okay? So, based on that being our imaginary root hanging from a string, we see that it's left heavy, so we have to do our rotation. So again, this is going to be a relatively simple one. Again, when you're doing the rotation, you don't have to redraw the entire tree on a test. Just draw the subsection you're going to rotate. And then, if you really want to abbreviate, you can just do like R and R and an LR, and I'll understand this right rotation and left rotation. You can do that too if you want to, you know, want to be like super efficient with your time. I'll put it fully though, because I don't want to get you lost. But yeah, so that becomes okay. We're still okay with the duplicates. And now that we did the rotation, we can just plug it back into the tree. So I don't want to have to write it again. So I'm just going to paste it down here. But you'd have to write it again on the test. And again, this is the part that we are now replacing with this. Okay? Just going to have to make this line a little longer. All right. So as you can see, the tree is okay for the most part. I mean, it's kind of getting a little messy, but yeah, you get it. Okay, so we have left to go the E and the R. Okay, so E and R. So where's the E gonna go? The E is gonna be smaller than the O, bigger than the A, bigger than the D, so it's gonna go there. So that is going to be a 1, 0, 2, 1, 3, 2. So that's a still balanced 3. Cool. No double rotations yet. But again, those are not going to be happening very often. And finally, we have one more letter. Will it do a double rotation? We shall find out. Where's it going to go? So it's bigger than O, less than Y, less than V. So dang it, it's like right here. It's like of all the places it could have been. Let's kind of redraw our tree out. D, E, B, R. Okay? That's probably not going to unbalance the root, but it is going to unbalance this subsection, as you can see already here. This is a 2, 0. So let's just rotate that bit. Yeah, literally all the rotations in this one were like right rotations. That's interesting. And then let's just plug it in. So let me copy paste. And then let's take that out and put in the rotated version. And there we go. So that's kind of what it would look like, the final version if you were doing this on the test. This exact example. So you start out with that. You insert, every time you do a rotation, you draw your rotation. You draw the updated version, and you keep inserting to that until you have to do another rotation. Draw the updated version, rotation, draw the final version, and then you are good to go. Just to confirm, let's just make sure everything's okay here. This is a 1, 0, 2, 1, 3, 1, 1, 2. So yeah, it is balanced. We're good to go. Okay, I'm not going to do the other examples this in detail unless we do double rotation. But I wanted to do one really slow to show you exactly what I'm basically expecting on the exam. So let's do Chewbacca now. And like, I hope that Chewbacca has a double rotation. Otherwise, we'll have to I'll have to improvise something. Okay, so C H. Oh, would you look at that? Would you look at that? I like Chewbacca now. Yeah, kind of coming and saving the day right now. I like it. I like it because as you can see here, this is going to be a double rotation. However, how, from a programming point of view, do we know it's a double rotation? We don't, actually. The only way we know is you just, in your code, you perform a single rotation, and then you see that it doesn't fix it. And then at that point, you have two choices. You can perform a double rotation on the new system, or you can do the single rotation to bring it back to the original, and then do your double rotation. I'm a little bit like picky about that. I like to have things brought back to the original version and do double rotation. You don't have to, but what you should do is you should be consistent about which method you use. So, so yeah. So what I'm saying with that is, step one here is like, okay, you don't. By the way, you wouldn't have to do this on the test. In the test, if it's a double rotation, you can just flat out show me the double rotation. But I'm coding wise, what you would do is you would try to rotate this. So this would end up like this. That would be the result of a single rotation on this. And of course, it doesn't fix it, right? So then, I prefer in code to run the rotation again to bring it back to what we had. So when you run the rotation again, so in this case, what I did is I ran basically a left rotation. And then you just run a right rotation. And then it basically brings it back here. Okay? So you bring it back to the start. I prefer doing that. Efficiency wise, probably not a good idea. But I don't know. It just feels nice to me. So it's just kind of a habit. Okay. So, anyways, the point is that the single rotation fails. So after you do a single rotation, put some Boolean variable somewhere in your class of your AVL, something, whatever code you have to do, flag it. Say, little red flag, whatever, that says, hey, I tried to do a single rotation on this tree, did not fix the problem. That's when you know that you got to call in your double rotations to the rescue. Now, which one do you call? Okay, let's look at them again. Actually, let's just bring it, since we're going to refer to them in a minute. Let me just copy and paste them again. So you look at your two rotations, and to pick between them, you just kind of look at the shape of the ZYX that you see here. So here it's the Pac-Man this way. I kind of drew it here for you as well, really tiny. But when the Pac-Man is looking like that, and when the Pac-Man is looking like that, that's what you decide. So you do a left-right rotation when the Pac-Man is like looking that way, so basically to the right, and when the Pac-Man is looking to the left, you do a right-left rotation. I don't know how you can remember that. Uh, other than that, like I don't know. There's a better like memorization technique than that. Okay. What I do know is that if you just look at the thing from a coding perspective, then you see whether it's left or heavy, right? So in this case, this is a right heavy tree. So if it's a left heavy tree, for example here, then you do the one that starts with left right. And if it's a right heavy tree, then you do the one that starts with right left. And that's what I personally do to remember it. If I'm doing it coding wise, if I'm doing it by hand, it's kind of obvious just based on the shape of it. Okay? But how we're going to fix that again is we have our CHE. So let's bring that down. Oh, and Geeks of Geeks has a nice article on this stuff too, so you should check that out if you want to see also more examples. But yeah, so in this case, you know that the problem child and the problem grandchild are these ones. So that's what we got to rotate first. Okay, we got to do the rotation and bring it basically this way. That's what we want to do. And so that single rotation, is going to be that X, Y, Z, but we don't have a Z, so we don't even have to worry about it. And we know that the final result should be something like this. Uh, I'm using X, Y, Z, but I feel like it's going to confuse you. So let me write this as a Z, Y, X, because I think that's what I was doing for that rotation on the sample on the top. Yeah, so we have this Z, Y, X, and so what you want to do now is you are going to basically ignore this X here, and you're going to take this right here, and you know that the final result for this is basically X, Y, Z. So again, you're going to ignore the X. So as you can see, all we're doing is we're flipping the direction of that. So you're flipping the order of the child and the grandchild. That's all this double rotation magic does. So once you understand that, again, this is all about understanding it more than anything. Okay? And so what you're going to end up doing here is you're just going to end up with Z, E, H, like that. Okay? That's going to be your first of the two rotations. As you can see, that is technically a right rotation, which makes sense because we have the Pac-Man this way, right? So we actually had this shape here, and now we have this shape. So we took the Pac-Man and we straightened them out by just beating the bottom of it like that. Okay? Now we all know how to do that. Very easy, right? We know that that is going to basically just be a single left rotation that is going to make either root and take that and be like that. Okay? So, yeah. And yes, for the 202 class, we do use C++ 11 or 17. Okay? Uh, yeah. All right. So, So far, we good. I hope we're good on this so far. You know. And as for the videos, you should be watching the CS 135, which is first basic programming, and then from there you go to 202, which is going to be more programming, object-oriented programming, and then you do data structures, which is this class, which is not really programming, it's more about the concepts of computer science. So, yep. Okay. All right. So moving on, we are going to keep just inserting now that we are basically inserted the first three, and I'm very glad that we had a double rotation because now you can see that double rotation with the AVL tree algorithm. So here you go. Okay. So the next thing to insert is going to be the W. So the W is bigger than the H, so it's going to go to the right of the H. And of course, you should always, always, always check the heights. Of course, you can do this programmatically, so you don't have to really worry much about this. And then on a test, I would play it safe and check them anyways, even though it might look okay, just so you don't accidentally, something's not balanced and you think it looks balanced, and then you rotate, and that kind of waterfalls into everything else being kind of messed up. So you don't want to end up in that situation. Okay, so now we're going to insert the next one, which is the B. So that's going to be all the way there because it's the smallest one. So here's another example of a tree that actually, well, depending on you ask, you might be like, well, this actually looks really balanced because, it has the same amount of nodes on each side. But to me, it looks weird because it's missing all the middle stuff. But it doesn't matter what it looks like. What matters is these numbers, and they are the same, so we're actually okay. And even after we insert the next character, which is the A, we're still okay because all that's going to get. Oh wait, no, we're not okay. See, I was going to say we're still okay, but we're not. Because now we are going to see that while the overall you might be like, oh well, if I was looking at this like from a perspective of just the root, you might be like, well, this is 0, this is 1, this is 2, this becomes a 3, and here you got like a 1 and 2 there, so you're like, oh, the E is balanced. So you might do exactly what I just did right there, which is to be like, oh, this still looks balanced, moving on. But it's not. It's not because this one right here is 2-0. So be careful that your eyes don't play tricks on you like they did to me right now. As I was trying to actually, as I was trying to tell you not to have your eyes play tricks on you, I bamboozle myself here and play tricks on my own. Okay? So this one's again just a simple rotation. I hope by now these are becoming, easy for you because you've done them a lot, and they're not, these are not so advanced because there's not that many children involved. The only times when the single rotations are tricky is if you got children. So like if these nodes all had children associated with them, like these two had children or something, and there somehow still wasn't unbalanced, that's when you gotta refer back to the algorithms to make sure that you know where the children go. Because every time that you do a rotation, a child can get change who the parent is. Let's take a moment to just make sure that we understand that. So when we got the left tree here, child 2 is the one that's going to get adopted from the parent. The grandparent's going to start taking care of them. As you can see, child 2 goes from being a left child of Y to becoming a right child of X. In the other example, we have child 3 being from a right child of Y to becoming a left child of Z. So one gets readopted, the other three stay the same. So when you're coding this, know that that means that one pointer can potentially change if such a child exists. If it doesn't exist, there's no readoption required. But you still want to put that, put it in an if statement basically. When it comes to the double rotations, each rotation can potentially, I presume, yeah, each rotation can potentially move one child. So a double rotation can potentially move two children. As you can see here, the first rotation is going to change who the child of X is for the left side. So 2 is going to be adopted by the Y, so again by the parent per se, but also the Y itself is going to become a child of X. So I don't know if you want to consider that a readoption as well. But since we're talking just about the 4 children here, which all the cases always deal with 4 children, there's still only one child being readopted, which in this case is going to be the 2. But when you do the second rotation on this to go to the final version, you do get again the 3 gets moved here. Okay? So first time the 3 stays here, but then it gets moved. So ultimately, from beginning to end, both the 2 and the 3 kind of get juggled around. So double rotation, 2 children can potentially change parents. Single rotation, 1 child. The other one's basically the equivalent of that. You can see here that that the 3 has to be readopted by the Y because now this is the child, so this has to be given to this. And then from the second part, you have the 2 going from the X to the Z. So the X is the one that basically like loses all its kids because they went to the gas station. Okay, so something to keep in mind. Again, the best way to verify if you're doing all of this right is that it should not break the binary search property, at least when you finish doing both rotations. But actually, no, anytime it shouldn't break it. Even with the double rotation, when you do one, it shouldn't break it. What might temporarily break is the height when you do the first of the 2 rotations. But other than that, the binary search property, where like things on the left are smaller, things on the right are bigger, that should never break. Okay? So, all right. Going back to this, we performed the rotation there, so all I gotta do is update my tree now. So let's just go ahead and update it. Actually, let's bring this back as well. So this is going to go away, and this is going to be replaced by our rotated BAC, like that. And then we check 1, 1, enter. So we're good. Okay, keep going. Let's go ahead and insert one of the C's now. So that is going to go to the left of the existing C. This is going to be 1, 0. This is a 2. And then this is going to be a 3. So this 3 is still balanced. Okay? Now I'm going to redraw the tree because in a minute it's going to start to get messy. So we got a C, and then we got a W. Try that again. And then we got a C here. Okay? So put that with the nicer one. Okay. So now let's go ahead and insert the second C. Oh, we just did actually. I guess we, yeah. I guess. Oh, no. We haven't. We haven't. I saw 2 C's and I thought we did, but no. Chewbacca has 3 C's, I guess. Okay, so let's insert that third C then. So that's gonna go right there, right? Because we want to keep that rule of thumb that binary search less than or equal to should be on the left side and then graded on the right. All the CCs there are going to get unbalanced, but this is the easiest rotation you have ever done in your life, right? Like there's just no way you could screw that up, right? I hope. Like if you ever get that on the test, like and you screw that one up, like I'm just gonna. Well, I'm not, but the TA will probably silently weep because they're all the same letter, right? So, I mean, yeah, like pop quiz, if your life depending on it, what is that rotation going to look like? Well, surprise, surprise, it's still just going to have a bunch of C's, but they're going to look like a triangle now. So there you go. Okay, so we got one more letter, which is the A. But before we do that, we got to check if the height's okay still. So I think we should still be okay, but let's just make sure. Yep, we're still okay. So now we just got to insert the A, and that A is going to go here, and I don't think that's going to unbalance everything because this is just going to become a 2. So we're still okay. So there you go. You only got to see one double rotation, but that's that. I still want to keep going on this tree though. So even though we finished inserting Chewbacca now, uh, I would like to insert more things. What time is it? By the way, I don't want to. So we got 5 more minutes, right? Yeah. See, I have the 2 hours plus here. It's already 7 here, so like I gotta do math because especially this weekend is the daylight saving switch here, but in Vegas it's in 2 weeks, so we're gonna be off by 1 hour. But then like when I come back, it's gonna be 2 hours again. It's gonna be weird. Okay, so let's just for the last 5 minutes just throw in a couple of numbers. 'Cause I want to show you one of these like massive nasty rotations. And I think we can achieve that by putting in maybe like another B. No, a C. Let's put a C here. Okay. So now this one's going to be 1, 0, 2, 3, 4. Yeah. Wow, this is a good one right here. So Chewbacca C. Okay. Yep. Time travel indeed. Okay. This is when you're like, ah, we gotta rotate like this is a nasty one. This is when you gotta pull out the algorithm to make sure you don't accidentally screw up something. Okay? So I like this. I like this. This is good. And all it took was inserting one more letter. So let's just do it like that better. Better usage of space. Okay? So you got to rotate what's wrong, right? So this is the one where like I honestly can't tell you right now. I have a suspicion that this is going to be a double rotation, but I couldn't tell you for a fact because like this could fix it too. Like I know that this is it's got that Pac-Man, but like this might as well fix it, and we have to follow the rule of trying a single rotation first. So we're gonna do a single rotation, and maybe it'll fix it. But I honestly can't tell you from seeing this like whether the single rotation will fix it or not, and much less with the code. So, okay, let's try it. So we know that this is what we got to rotate. And this is where it actually, we have to have that visual aid. So we know that this has to have, this time I'm going to pull the algorithm because I want to make sure I don't screw up the children, as should you. So here we got what we want to do. And we have all the children denotations there. So make sure that we don't, we got to think about the children, basically. So we know that XYZ is going to become XYZ like that. So we're going to make new root be the B. And then this is going to be the A, and this is going to be the E. And now this is where the algorithm is great. You just look at that to see what each of the children should go. So like those two children are technically this A and then this non-existing one. So that means that those are going to be the same. So there's going to be an A here, nothing on the right side. And then let's just take care of the C stuff. So that is going to be this one. So that is technically this stuff here. So that is going to stay basically in the same spot. So we just put H and W to the right of that. And again, the way you're going to verify if this worked is if you make sure all the nodes are still following that binary search property, nothing's backwards. And finally, this is the cool part. So we know this is the one that actually swaps areas. So this whole thing is going to be the one that gets readopted from the B to technically what is the C, which is actually the E. So it's going to get readopted right here. Okay, so that means the C is going to go there. And I don't want to screw it up, so I'm going to copy paste it. So literally from there, it's going to get readopted to there. Bam. Now, whether this fixes it or not, we're about to find out. But that's actually that. So see, it's very nice to be able to see the algorithm for these where children are involved, because otherwise you might screw it up. Okay, so this is a 3. So you got 1 and 2, and this is a 4. So yeah, I did not fix it. Okay, so yeah, so this will be a double rotation. But you see, this is something that like was not 100% clear about. Like it could have been okay. Like we were really close, but not close enough. Okay, so that's fine. We just do the same rotation to bring it back, which I'm going to skip for time. And let's just go ahead and do the double rotation so we can get this fixed and then be on our way. Okay, so we know that the single rotation failed, so we rotate back to bring it back to the beginning. Or you could do the double rotation on the new version, but like I said, I'm not a fan of that. So, okay. Again, I am not going to rely on trying to do this, especially with double rotation, intuitively like that. I'm going to just pull out my algorithm and make that do the work for me. So, shrink it down, put it here. We can see that this is what we have. So we got to rotate what's on yellow there. So the yellow is basically going to be the B and the C are going to get rotated like that. So we don't have to worry about the EHW for now. We just have to worry about that. So we get the B and the C. And then for worrying about all these children that we have, all the A's and C's that we have, we're just going to look to see where they are in the algorithm. So we know that this one doesn't change. So whatever's on the left of the B is not going to change. The two A's are not going to change. Uh, wait, the B. Hold on, hold on. Oh, no, no, no. It got flipped this way. That's right. I didn't flip it like that. See? See, you got to be careful here. See, and it's a red flag when things are out of order. That's the way it's got to go. Because the B here is going to go, which is the Y, goes to the bottom. So that goes to the bottom, and this X goes to the top. So the C goes to the top. So that's what we're starting out with. Okay. So now the children on the left, which are all the stuff in orange, is basically this. So that stays the same. So we're just going to put A. Okay. And then we're not dealing with the Z stuff here. So this up here is still an E, and it's got the H and the W. We're not worrying about that right now. We do have to worry about 2 and 3, which do exist. I'm going to color code them to not get lost. This is technically 2, and then this is technically 3. Okay, so as we can see on the result, the 3 here, we can see that the 2 stuff is going to get moved around. It's going to get moved around from the C being there. It's going to get readopted by the Y. So it's going to get readopted by the B in a different direction. So that means that here we're going to have the 2 C's from there. And then finally, the X should not get readopted. It just got moved. The X is 3 number. So this one does not get readopted. So that means the C does not get readopted. So it just goes up here. Okay? So now we've done one of the 2 rotations. Okay? How do we know which double rotation to do? You just see which side is heavy. So the left side is heavy here. So we need to do a right one. So we do right left. Okay? So in this case, or sorry, right left, left right, because it's left heavy. So you do left right. That's one way to remember. Or look at the Pac-Man and then compare it to what you have there. So you can see here, you're going to do the left right rotation whenever you have something like this. You see how the left is heavy there? That's what we have right now. 4-2. I mean, sure, it's 4-2 instead of 2-0, but that's the same idea, right? So just look at those tiny numbers in the algorithm that I put for each one, and that's the reminder. And then just put that on your cheat sheet or on your code. Okay? So, all right, cool. So we did one of the 2, so now we got to do the second one. So that one's more trivial, but still difficult because we got a bunch of children involved. But now we just got to do a single rotation on this, which is what we're doing here. Okay? So that means C is going to be the new root. And then B and E are going to be to the left and the right of that. And then we just got to move the children around. So of the children, you can consider these to be the children. So this is children 1, children 2, children 3, children 4. Of these, the only one that's going to get readopted is children 3. That's this one. So the other ones we can just copy and paste. So the A's and the C's are going to go here. A, C, C. And the H and the W are going to stay. And the only one that gets readopted is the C. It's going to go from the C, from the one in blue. It's going to go from here, and it's going to get readopted to the left of that. So that means to the left of the E. Like that. And so this is where things get kind of nasty with duplicates, because you can see that the C here being here is like I'm not very happy about that right there. Because technically, yes, this is legal, but I don't like my duplicates being like that. So the AVL tree and duplicates are not fans of them. But technically, the tree's okay. Technically. You're just going to run into some issues with that. But yeah, so now we can see that if we go and do the math to this, 2, 1, 3, 3. It is perfectly balanced as all things should be. So we have fixed it. I did go a little quickly at the end there, but we are out of time. So just go ahead and rewatch that if you're still stuck. And if you really want, I can redo that example at the beginning of next class on Wednesday. But yeah, that's that. I like that last example because that shows you with children how it can get tricky. But this is interesting because like it gets tricky with by hand. But if you code it right with a simple example, the programming handles even the harder examples very very easily. So that's more tricky for us doing it by hand. But as long as you follow the rules, you'll be okay. And like I said, the only exception with AVL is with duplicates. I don't like this C and this C being there like that. Not a fan of that. But you know, that's just what the algorithm gave us. Yeah. It's basically saying that like this wouldn't have really worked otherwise. Um, no matter what you do, like there was no other way that this tree could be built and be balanced with that amount of duplicates. Okay, so yeah, this is like I said, one of the harder algorithms. So congratulations for making it through. We spent so long in this that it became dark outside. All right. I know in Vegas it's probably still light, but here the 2+ hours it's dark. Okay, we're already past our time, so I am not going to extend this longer than it has to be. So thank y'all for watching, and hope you all learn with AVLs. Next time I think we changed topics. I think we do hashing if I recall correctly. Let's see. Oh no, we do heaps first. We're gonna do heaps. So more tree stuff. We're not done with trees yet, but heaps are much nicer than AVLs in terms of coding. So all right. Well, I hope you all have a good rest of your evening or afternoon, and I will see you guys on Wednesday. Thanks for watching and stay safe. Bye, everyone.